Hello, pre-calculus student. This video is part 2 of 4.7 exponential application. And in particular, we want to look at a general continuous growth or exponential growth or decay. And we want to find time to achieve a certain value, not just for investment, but for population or any like radioactive compound. Before we go into that, we want to review the form model that we can use. Usually we, like what I have said before, if a growth model is written in A0 e to the kt, which is continuous growth, we could actually solve it better. So sometime we would use the growth rate or find the continuous growth rate to write the growth models or decay model as y equal to a0. A0 is the initial amount, and instead of 1 plus RT, we write as e to the kt. At the end of the lecture, we'll talk about how to convert between them. But in general, we prefer, if we are to analyze a exponential growth, we want to write it as e to the kt. In the strict, like in layman's term, people do not want to know about K or the ray. They want to know about doubling time or half-life. So we can also write a models to find the amount after t years or t unit of time. The model is A0 2 to the power t over the doubling time. So if doubling time is given, instead of y equal to a, b, t, we would use a0, which is initial value, times 2 to the power t over the doubling time. And for half-life, it would be a0. Instead of 2 being the base, it's 1/2 t to the h. Now, this model makes sense if you just think about you plug in the doubling time t, right? Then this would become t over t is 1. So A0 times 2 would be y. You actually double. The same for here, if the material, the radioactive compound, has a half-life of h, you plug in t equal to h, you become A0 times 1/2. You actually call the y is 1/2 of it. So now, how do I convert between them? Earlier we say Lm 2 over r is actually the doubling time. So we're going to prove it. Okay, so to prove it, say I have a formula of A0, A equal to A0, e to the RT, or KT, which is K is the continuous rate. And I'm going to divide, so for add T, okay, so yeah. And let's plug in at t equal to the doubling time t. A would become half of AC, 2 of A0, doubling, right? Doubling. It would become 2 times of A0. So this is what we know for t is a doubling time. Okay, so you would write 2 of A0 would equal to A0 e of k times the big T, which is the doubling time. And then the T A0 and A0 cancel. If you divide both sides by this, you have 2 equal to E of KT. How do I solve it? I can do ln2 will equal to ln E of K capital T. Capital T move out, so ln2 will equal to the move to the front is K times T. So you can see K would equal to ln2 over T, or T is equal to ln2 over K. So this is the relationship between K and T. You can easily convert between them. And earlier when the K was the ray, we can tell the doubling time. The same for half-life. Let's say H is the half-life of a compound or prescription drugs or something. And so at T equal to H, the A would become 1/2 of A0. We plug into the formula, right? Supposingly A is A0, E of KT or RT. Now A is 1/2 A0, and this is A0, E of K times the H, which is half-life. T is equal to H. And then we do just the same thing. We divide by X0, divide H0. You can say 1/2 is equal to E of KH. Ln both sides, Ln 1/2 would equal to Ln E of KH. And this move to the front, Ln E is 1. That means Ln 1/2 is equal to K times H. And you can come up with the formula. If you want to solve for H, then when you go to Ln2 over K, if you know K, and if you don't have K, you only have H, it will be Ln2 over H. So it's very convenient to convert between them. So either you know K or you know Ln, or you know half-life, you can convert between them. So let's do some example. So just remember these two very useful conversion and also the two model. Example 3, a population model is given by P 25,000 e to the 0.25 t. So this is the A0 e to the kt situation. How long would it take to reach 1 million? So this would be P, right? And we want to know time is equal to what? And we have this. So we would write 1 million on this side. Excuse me. Equal to 25,000 e of 0.25 t. To solve for t, we divide 25,000 on both sides. If we cancel the 1,000 and then simplify it, that's equal to 1,000 divided 25 is what? It's 40. Okay. So we say 40 equal to e to the 0.25 t. That's very easy to do. So we can add ln on both sides. ln 40 now equal to ln e to the 0.25 t. Move to the front and ln e equal to 1. So ln 40 equal to 0.25 t. So t is equal to ln 40 over 0.25. So put in the calculator ln 40 divided by 0.25. That's a lot. 14.7 or 14.8 years. But this town's population is growing 25%. So that's what's the doubling time? Oh, we know K, so it will be ln2. Doubling time is equal to ln2 over K. That's ln2. Our K is 0.25. Should be very fast because you grow ln2 divided by 0.25, 2.8 years. Yeah. Every year is already increased 25%. So 2.8 year, it will be double. Okay, so you can use this. You don't have to solve another one. If it is reaching another value, you have to solve. Example 4, a population of bacteria is growing continuously at a rate of 35. So if I know continuous rate, so this is K. K is 0.35 and it's for hours. Write the exponential function that model it. So I would say that P of T is equal to A0. This is A0. 800 e to the 0.35 T. That is the population. how long would it take grow to 6,000? So that means P of watt equal to 6,000. So I'm going to plug in 6,000 on this side, and this would be 800 E of 0.35T. Solve it as before. Divide by 800. 60 over 8 equal to E 0.35T, and you know what to do, ln on both sides. 60 over 8 would equal to ln E of 0.35T. And the 0.35 move to the front. That's like what we have done all the time. That means ln 60 over 8 is equal to 0.35T times ln E, which is 1, right? So then T would be ln 60 over 8 divided by 0.35. Time to put in the calculator. ln 60 over 8 divided by 0.35. 5.8 years. Oh, 5.8 hours. Go to T. What? 5? 5? Oh, 5. I write 3. $35, right? Let me make sure that it is 0.35. Oh no, this should be erasing. Oh, okay. 5. Oh gosh. Okay, put back. It's rather comes to 5.8 hours. So the unit is not time, is not year, but what is the doubling time? So we know K is 0.35. So the doubling time will be ln 2 over 0.35. That should be very quick, right? I think like less than 2, maybe 2 years or so. ln 2, oops, sorry. ln 2 divide, have to close it, divided by 0.35. 1.98, yeah, 1.98. Around 1.98 year. If you want 2 decimal places, or it will be not year, hours. Sorry, I always make that mistake. 0.98 hours, or around 2.0 hours. Okay. So let's do what time is it? So in the next video, we'll do a video on half-life, things that are decaying. We will find half-life and also find time when it decays to a certain value. Yeah. So watch the third video.